Now let's talk about how computers think in a turn-based game. What the computer is going to do is it's going to simulate every possible move from our board that we start at when we call our function to find out what we want to do. And then from there, it's going to keep on calling that function on those possible boards until we either reach the end of the game or we go too far and we decide, alright, here's where we stop. And the reason we have to tell the computer to stop at some point is because, well, it would take too long to calculate every single possibility. Especially at the beginning of the game, you don't want to go all the way to the end of the game. For example, in chess, there are 400 possible scenarios just in the first two moves. And the number of possible scenarios just gets bigger as the game goes on. It's also possible for two pieces to just go back and forth over and over, and the game would never end going down those routes. So we have to tell the computer that at some point we have to stop checking our possible moves. And then when we finally get to the end, we're going to give that move a heuristic, or a estimate of how much this board is worth to the AI. So you might be thinking that once the computer has found all the possible scenarios, it would go straight for the highest value. In this case, it would be this 6 right here. But that's not true. In a game of tic-tac-toe, for example, the fastest way for the AIs to win would just to go 3 in a row like this. But obviously the player isn't going to let the AI do that, so if the player goes here and then the AI goes here, the player is obviously going to go over here to stop the AI from winning. So we can't just assume that we can go straight to the highest value. What we have to do is instead alternate between simulating our AI's move and our player's move. So you see now the colors alternate between blue and gray, blue representing the AI's turn and gray representing the opponent's turn. Now one thing that might be sort of confusing is that these possible boards, they don't all exist at the same time. So what I'm going to do is get rid of all of these lines here connecting them, and I'm going to use these lines to represent the boards that actually exist. So what the minMax function does is it gets all of the possible moves and then it goes through each of them. So first, from here, we are going to go down to our first possible child. And then we're going to ask that child if the game is over at this node, or if we have gone too far. In this case, the game is not over and we have not gone too far, so this child is going to ask each of its children the same thing. Is the game over here, or have we gone too far? Both of these being no, so now this one asks its children the same thing. And in this case, we have either gone too far or the game is over. So at this point, we evaluate this node, and we get a heuristic value of 5, so this is worth 5 points to the AI. Now we pass this value back up to its root node, and then when it gets back to the root node, it says, alright, well, are we minimizing or are we maximizing? Or are we the AI or are we the AI's opponent at this point? And blue represents the AI, so we are the AI, so we are maximizing. So what we're going to do when we're maximizing is we ask, alright, well, the value we got, is it greater than the value we used to have here? And in this case, we don't have a value yet, so we can just say this one is now 5. Going down this path gets us a heuristic value of 5. This node still has possible moves though, so we go down to the next possible move, and we evaluate this child, if the game is over, or if we have gone too far. And for the sake of simplicity, I'm just going to say all of these have gone too far, or the game is over. So now we evaluate this node, and we get a value of 3. We pass this 3 back up to the root node, and we ask, are we maximizing or are we minimizing? And again, we are the AI, so we are maximizing, and since 3 is less than 5, we're not going to change the value of this node. So we don't care about this route at all. And going down this path, we would still be aiming at this 5. Now we've evaluated every single child for this node, so we pass this back up to the parent of it. Now this node is the opponent, so we're minimizing at this particular node. So what we're going to ask is this 5 less than our value that we had before? And we don't have a value yet, so we can just say this one is now 5. And the reason this is minimizing is because it's the opponent's turn. So the opponent is trying to minimize the value that the AI can get. So now that we've evaluated this first child of this node, we have to check the rest of the children. So we go down here, and now this node exists, and then we have to evaluate each of its children. So it goes down over here and it says, alright, we have a value of 2. This gets passed up over here, and we are maximizing, but we don't have a value yet, so we say this is now a 2. We go down to the rest of its children, we get a value of 6. This gets passed up to our 2, and since we are maximizing in this case, this node now knows that it is now a 6 instead of a 2, because 6 is greater than 2, and now we don't care about this 2 anymore, so we can get rid of this node over here. Now this node passes its value up to its parent node, which is minimizing, and since 6 is greater than 5, it wants to get the lowest value, so it stays at 5. So we don't care about this. Now this 5 passes up to the root node, and this root node is maximizing, but we don't have a value yet, so we can just say this is a value of 5, and then we have to check the rest of its children. And then this has to check its children, and this has to check its children. And then this 4 gets passed up to the root node, which is maximizing, we get a value of 4. And then we look down over here, we say, alright, this is 2, 2 is less than 4, so we don't change our path. This 4 gets passed up over here, we get a value of 4. And now we checked all of these children. This 1 gets passed up over here, gets a value of 1. And then we check this child, we get a value of 4, which is greater than 1, so we now change to 4. This 4 gets passed up to this root node, and they're both 4. So, for the sake of simplicity, what we're going to say is if the values are equal to each other, we're just not going to change our path. So, we're not going to change it from going from here to here when we go down this path. And then this 4 gets passed up to the root node, but since this root node is maximizing and 4 is less than 5, we don't care about this 4 at all. So, now the final path we're going to take is going from this node to here, here, then here, instead of going towards this 6. We're going to go for this 5, because we're assuming that the AI's opponent is going to do everything in its power to make us get the lowest score possible. So going for this 5 right here is the best possible scenario for our AI if the AI's opponent plays as best as possible. Now, you might be thinking, that seems like it would take a long time, going through every single possible move until we reach the end. And you would be right. So what we can do is something called alpha-beta pruning. And I'm not very good at explaining this. I'm going to put a link to a video that is much better at explaining this in the description, because there are a lot of videos out there trying to explain alpha-beta pruning, and most of them aren't very good. But I'm going to try to explain it anyways. So let's get rid of all these connections. And we're going to start the same way as before. We're going to go through each of our children. So we go down here, and we don't have a value or anything yet, so we're going to keep on going down its children until we reach a node, and we're going to get this value of 5, and this 5 is going to get passed up to the parent, and we're going to say, alright, well, we don't have a value yet, so we're going to be 5. And then we're going to look at the next node. And we can't do any alpha-beta pruning yet, so we're going to look at it, and we're going to say, alright, this is 3, 3 is less than 5, so we're going to stick with 5. 5 gets passed up to the parent, and then this becomes 5. Now we're going to look at its children, and we haven't ended yet, so we can't do alpha-beta pruning yet. And we're going to look down at the first children, and we get a value of 2. Now this 2 is going to get passed up over here, and we get a value of 2. Now at this point, because this node has a parent that has a value, we're going to ask this node from the perspective of its parent if we're going to prune the rest of this node's children or not. So what we're going to do is we're going to say, alright, well, this child is maximizing. In other words, no matter what happens, this node is going to get a value of 2 or greater. So no matter what the rest of this node's children are, the value is going to be 2 or greater. And then we're going to look at our parent's node, and we say, alright, well, we have a value of 5 right now, and we are minimizing. Because this node is going to return a value of 2 or greater. Is 2 or greater less than our 5? And the answer is yes, therefore we keep checking children. So we can't do any alpha-beta pruning at this point. So now we have to keep on checking children, and we get a value of 6. This is maximizing, so now this 6 gets passed up, and this becomes a 6 or greater. Now we look from the perspective of our root node again, and we say, alright, well, this node is now a 6 or greater, and our node right now is a 5. Since 6 or greater is greater than 5 and we are minimizing, we're not going to care about the rest of this children, and we're not going to go down this path at all. So if we imagine that this actually had another child, let's pretend that this child's value is 1, for example, and we haven't checked it yet. We're not going to bother checking it because we know that this node right here isn't going to select it, because it's always going to select something that is 6 or greater. So this value over here gets pruned. We don't care about checking this. If these values were in reverse, so this 2 was on the right side and this 6 was on the left side, and the first value checked was this 6, so this 2 wasn't checked at all, then we would be able to prune this 2 as well. So we would never have to bother checking these 2 nodes because we know we're not going to go down this path. So when you are doing your alpha-beta pruning, it is better to organize your nodes based on their heuristic value from greater to least, or least to greatest, depending on circumstances. But we're not going to bother doing that because it's, well, too hard. Especially in a Othello game where the values can get flipped around very, very quickly. But that's just something to keep in mind when you're doing your own games and you're doing your own alpha-beta blending. So now that we know that we don't care about this, we're going to pass this value up to our root node. We don't have a parent, so we're just going to say this is 5, and then we check each of its children. So we go down here, this checks its first child, this checks its first child, and we get a value of 4. 4 gets passed up over here. Now we're going to check the rest of its children, and we get a 2. 2 gets passed up, 2 is less than 4, so 4 stays as this value. This gets passed up over here, And now we say, alright, well, this is 4 now. And we know that this black is always going to be minimizing. So we know that this value is always going to be less than or equal to 4. And we look at the parent node, and the parent node right now is 5. Going down this other path can get us a value of 5. And going down this route would get us a value that is less than or equal to 4, which is obviously less than 5. So we don't care about the rest of these nodes over here, because no matter what these values are, even if this value over here was a 9, for example, really high value, black is never going to choose this 9. So it doesn't matter what these are, this value is always going to be less than or equal to 4. So we can prune the rest of these nodes over here, and we can just say, alright, well, we don't care about this route. Now we have our values because we've checked all of the children that matter. So we know that we're going to go for this 5 over here, starting at this board. So by doing this alpha beta pruning, we've already cut off 1, 2, 3, 4 nodes. And this value will get greater, obviously, depending on how many possible moves there are. So in Othello, in your very first turn, there are 4 possible moves, not 2. And your possible moves will obviously get greater or smaller, depending on circumstances. But normally there will be more than 2 possible moves per board. So we can save a lot of time by cutting off the moves that don't matter at all. Now let's actually create our min-max function. We are going to create a new function, and this is going to be called, let's just go with min-max. And this is going to require a couple of inputs. First off is our graph, because we need to know, obviously, what the board looks like at this point. And then we need our current depth, which is an integer that is going to count down. So when we first call our min-max function, it might start at 4, for example. And then every time this calls the min-max function on its children, it's going to reduce the depth by 1 until it eventually reaches 0, which is when we are going to break out of our min-max being called. Now we're going to need our alpha and our beta values, which are going to be used for our calling to stop checking if we, well, don't need to check the rest of our children anymore. After that, we need a boolean, which is going to be if we are minimizing or maximizing when we call this min-max function. And I'm going to call this maximizing. And this is going to be saying, alright, when we call this min-max function, is it from the perspective of the AI, or is it from the perspective of the AI's opponent? And now we need one last boolean, and this is going to be if we are player 1. AI is player 1, question mark. Because we need to know if the AI is player 1 or not to properly evaluate our board. Let's also add some return values because we need the heuristic to be returned when we call this min-max function if we are returning when the graph has a game over or we've gone too far in the depth. So we need to return an integer, and we'll just call this our heuristic. And then we also need to return our actual move. So this is going to be our int point, and we'll just call this move. And we have to return the move because if we don't, then all we're going to be returning is our heuristic, which doesn't help when we actually have to find out which move the AI is going to make. Now, first thing I'm going to do is promote our alpha and our beta to local variables because it's going to be a very messy graph unless we do this. So let's promote these to local variable. I'll call this local alpha and local beta. And after that, we need to check to see if our depth is equal to 0. So if we are breaking or not, so equal to 0. And this branch here is checking to see if our game is over. So the other way the game can end is if there are no more possible moves. So off this graph, we're going to get our possible moves. And the boolean is player 1 for our get available moves. It's going to be is our maximizing equal to our AI is player 1. So now this branch is going to check to see if we have no possible moves or if our depth is equal to 0. And at this point, if this is true, then we're going to have to return our heuristic and our move. And we don't actually care about returning our move at this point because it doesn't matter when we return from here, but our heuristic, well, we need to create a function to get our heuristic based on this graph. So let's create a new function, and we'll call this evaluate board. And this evaluate board obviously needs a board to evaluate. And then we also need to know if we are evaluating the board from the perspective of player 1 or player 2. So let's add a new boolean, and this is just going to be is AI player 1 or player 2. So let's add a new boolean, and this is going to be our, let's say AI is player 1. Finally, we're going to need another boolean that's just going to ask if the game is over or not. And the reason we're going to ask if the game is over is because we are going to return values based on if the game is over. For example, if the game is not over, then we're going to return a relatively smallish number. But if the game is over, we're going to return either a huge positive number or a huge negative number. Because we want the AI to know that winning or losing the game is a huge deal compared to just continuing to play. So first thing we're going to do is branch on if the game is over. And if the game is over, then what we're going to do is return a score based on the graphs and if the AI is player 1. So off this graph, we can get player pieces count, and if player 1 count is greater than player 2 count, then we know that player 1 won. However, because we are using an even amount of pieces, it is possible for there to be a tie. So let's do an equal, and if we tied, then we're just going to return a value of 0 because that's neither good nor bad for our AI. So on this true, let's do a return, and we don't have a return value yet, so in our evaluate board, let's add a new parameter in the output. It's going to be an integer, and we'll just call this our heuristic. And if the game ended in a tie, we'll just return a value of 0. Otherwise, we are going to return a value based on if player 1 won and if the AI is player 1. So if player 1 won, and if player 1 won is equal to our AI's player 1, then we're going to return a relatively large value, and otherwise we're going to return a relatively small value. Now, why are we checking to see if these are equal? Well, that's because there are 4 possibilities. If the AI is player 1, and if player 1 won, then these both have 2 possibilities, and it's represented in this board right here. So if the AI is player 1, so this check mark, and then the player 1 won is not true, this X, then we're going to return a low value. Let's go with negative 10,000. However, if AI is player 1 and player 1 won, then we're going to return a positive 10,000. Now, if AI is not player 1, in other words, it is player 2, and then player 1 did not win, in other words, player 2 won, we're going to return a positive 10,000. And if AI is player 2 and player 1 won, then player 2 lost. Therefore, we will return a negative 10,000. So you'll see that the only times we return a positive 10,000 is when these are both X's or when these are both check marks. If one of them is an X and one of them is a check mark, then we return a negative 10,000. That's why we're going to check to see if these are equal to each other. So if the game did not end in a tie, we're going to return a value. Let's do a select, and that select's wildcard is going to be this equals, and if they are equal to each other, then off this true, we're going to return a positive 10,000. If it is false, we're going to return negative 10,000. Now that takes care of evaluating our board if the game ended. However, if the game did not end, which is going to be most of the scenarios, then we need to evaluate it slightly differently. Now, what we could do is get our player pieces count and just subtract one of these from the other, depending on if we were player 1 or not. However, that would mean that our AI only cares about the number of pieces on the board rather than their position on the board, which actually matters a lot in Othello. For example, if you look at these center pieces, this white piece can be captured in 2 ways. We can capture it horizontally by placing a move here, or vertically by placing a move here. The same applies for any of these pieces that are in the center. So this piece can be captured horizontally over here, or vertically by going up and down. However, if black were to go here, we now have a piece on the edge. And this piece on the edge cannot be captured horizontally, because even though there's a white piece over here, white can't go on the other side to sandwich it, because it would have to go outside of the bounds of the board. The only way for white to capture this black piece is to go vertically, so it would have to go up and down over here. So the chances of this getting flipped is significantly lower than if it was on the center of the board. So pieces on the edge should be worth more than pieces on the center. This is even more true for pieces on the corners of the board, because corner pieces can't be captured at all. Even if white were here and here, white can't go on the outside of the board horizontally and vertically to flip this black piece. So because this black piece can never get flipped, but it can still be used to capture other pieces, it's going to be worth even more than the pieces on the edge of the board. So to evaluate all of our pieces, first we need a local variable. This is going to be an integer. Well, let's just call this our local heuristic. And what we're going to do is go through every single piece in this graph, and then based on if it is player 1 or player 2 piece, we are going to either add or subtract to our local heuristic based on its position. So let's get our for each chord macro that we made earlier. We are going to get our graphs at that index, so get a reference. Now, if the slot at this chord is not equal to anything, so if there is no piece there yet, then we don't really care. So let's do a not equal, and off this true, so if there is a piece on that chord, then we are going to either add or subtract from our local heuristic based on if it is player 1 or player 2. So we are going to get our AI is player 1 to enum, and we'll ask if this is equal to the piece that we found or not. And if it is equal to our AI is player 1, then that's a good thing. And if it's not, then that's a bad thing. So we are going to either add or subtract from our local heuristic based on this boolean. So let's do a add to our local heuristic and set our local heuristic equal to that add. And off this add, we're going to do a multiply. Now in the top part of the multiply, we can do a select, and the index for our select is going to be our equal to here. So if our player2enum is equal to the piece at this chord, that's a good thing. So our true is going to be 1, and our false is going to be -1. So we're just going to subtract the same amount or add the same amount of points based on if that piece is our piece or not. Now for the bottom part of this multiply, we need to get our value based on if it is in the center of the board, the edge, or the corner. To get that, we just need a couple of Boolean checks. We're going to ask if our x or our y is equal to 0, and that's going to return true if it's any of these. So x is going to return 0 on this row, and y is going to return 0 on this column. And then we need to check to see if our x or our y is equal to our board size minus 1. And that's going to return this column and this row up here, which returns all of our border pieces. Now to get if they are in the corner, we're just going to do some more AND checks. So if our x and our y is equal to 0, then that's going to be a corner. If our x is equal to 0 and our y is equal to our board size minus 1, then that's going to be another corner. If our y is equal to 0 and our x is equal to our board size minus 1, then that's going to be another corner. Otherwise, if our x and our y are equal to our board size minus 1, then that's going to be the final corner. So if any of these are true, then that's going to be our corner pieces. But if any of these are true, it's going to be our border pieces. So we need to do some ORs based on these pieces. And for our b in our multiply here, we're going to do a select. And this first select wildcard is going to be if we are on the edge or not. So if this is true, then we're going to return something. Otherwise, if it is false, so we are in the center, we're going to return a value of 1. Because we don't really care if it's in the center. It's not going to be worth that many points. However, if it is true, we need to do another select, and the index for this select is going to be if we are on the corner or not. And if we are in the corner, then we're going to make it worth 7 points. Otherwise, if we are not in the corner, in other words, we are on the border, we're going to make this be worth, let's say, 3 points. And assuming I plugged all these in right, it should give us a point value of 1 for everything in the center, a point value of 3 for everything on the edge, and a point value of 7 for everything on the corner. And then once we have that value, we're either going to multiply it by -1 or by 1, depending on if that piece that we found at that chord is good for our AI or if it is bad. And then we're going to add that to our local heuristic, and then at the very end, when we've gone through every single chord, we are going to return our local heuristic. So we just add a return here and plug in local heuristic. Now that we have our heuristic, we can go back to our minMax function, and when we do our return, we're going to return our evaluate board, and this can actually be a pure function because we're not going to be really getting our heuristic from it many times. So let's plug our heuristic in here, and for our graph, it is going to be the graph. Our AI is player 1 is going to be if our AI is player 1, and if the game is over, it's going to be this equals over here. If our available moves length is equal to 0, then the game is over. And that returns our heuristic when we either get too far in the game or if the game is over. Now we need to do our false in our branch to see if we are breaking or not. Because if we are not breaking off of here, we need to do some more stuff. To when we were looking at our graph, when we were explaining the minMax function, we had to set our current route based on the best child that we had. So to find our best child, we're going to need another local variable. It's going to be an integer. Let's just call this our min/max eval. And the first thing we're going to do off this false is set our min/max eval based on if we are minimizing or maximizing. So let's do a select off this set. And if we are maximizing, then we want this to be a negative really no number. Let's go with 1 million or something like that. And if it is false, we want this to be a really high number. Because if we are maximizing, then we want to get our highest value. So we want to start with a really low value at first, so that the very first child we check gets set as our best child. Otherwise, if we are minimizing, then we want to get the lowest value. So we want to start with a really high value so that the very first child gets set as our lowest value. Now that we have our min/max eval, we're going to do a for each loop with break off of our get available moves over here. And the reason we want to do a for each loop with break is because this break is going to be called when we call the rest of the moves that we don't have to check. So when we're going through each of our possible moves, what we're going to do is simulate our board based on that move. So let's simulate our move. The graph is going to be the graph that we passed in. The move is our array element in our for each loop with break. And our isPlayer1 is going to be this is our maximizing equal to our AI isPlayer1. Now that we have our simulated graph, we're going to have to call our minMax function on this graph. The depth is going to be our depth that we passed in over here, -1. The alpha and the beta is going to be our local alpha and beta. And our maximizing is going to be slightly special due to the fact that in Othello, it can be your turn twice in a row. If the opponent doesn't have a move available, then it's still going to be your turn after you play. So we're going to have to account for that. But our AI isPlayer1 is always going to be the same. So our AI isPlayer1 over here is just going to plug directly into our AI isPlayer1 over here as well. But for the maximizing, what we're going to do is drag off here and do a select, because it's just going to be easier to do it that way. And off this simulate move, the simulated graph, we're going to have to check to see if the other player has an available move after we've done the simulated graph. So in this simulated graph, let's do our get available moves. As for the boolean for isPlayer1 in our get available moves, it's going to be the not of our simulated moves isPlayer1, because we want to check for the opposite players. So off of this equals over here, we are going to do a not and pass that into our isPlayer1 for our get available moves. Then we need to check to see if our available moves for our opposite player is greater than 0. And that greater than 0 is going to be our index wildcard for our select for our boolean for if we are maximizing or if we are minimizing. So if our get available moves returns a length that is greater than 0, so if our opponent can play a move, then on this true, we are going to return the not of our maximizing. We want to reverse our maximizing. However, if it is false, so if the opponent does not have an available move, then we are still going to be maximizing if we are maximizing, and we're still going to be minimizing if we are minimizing. So we can just plug this directly into our false. Now that we have our min-max, we are going to have to do some stuff with our heuristic and our move. First, we're going to branch on if we are maximizing or not, because if we are maximizing, we want to, well, maximize, and if we are minimizing, we want to minimize. And let's start with if we are maximizing. So if we are maximizing, then we are going to get our min-max eval and ask if the heuristic we just got is greater than our min-max eval, because if it is, then we need to update our information about what our eval is and our best move. So let's do a branch over here, connect our true to this, and on this true, we are going to set our min/max eval equal to the heuristic we just got. We also have to save our best move at this point, so let's make a new local variable. We'll call this best move. And this is going to be an int point because that's what our moves are. And set our best move equal to the move we just got off our min-max function if it is true. Either way, on this branch, if it is true or false, we need to set our local alpha equal to the maximum of our local alpha and our heuristic that we got from our min-max function. Now I'm sure you're wondering why we're doing this, and I would love to explain it to you, but I'm honestly not very good at explaining it, and I would probably just make you even more confused. So I really highly recommend watching the video in the description if you want to understand what's going on here. Now we need to do another branch to see if we're going to break out of our for each loop or not, because we don't want to go through every single children if there's no point in doing that. And the condition for this branch is going to be if our local beta is less than or equal to our local alpha. And if this is true, we can connect the true into our for each loop with break. Now we're basically going to do the opposite of this up here in our false branch for if we are maximizing or minimizing. So in the false, we're going to do another branch, and this branch is going to check to see if our heuristic is less than our max/min eval. And if it is, then we are going to set our max/min eval to be our heuristic that we found, and we're going to set our best move to be equal to that move as well. Either way, we're going to have to set our local beta to be equal to the minimum of our local beta and our heuristic. And then once again, we have to go to our branch to see if we can break out of our for each loop with break or not. And once we've actually finished doing all this stuff, we are going to, in our for each loop with break on the complete, we're going to return the heuristic and our move. The heuristic is going to be our min/max eval, and our move is going to be our best move. And that actually does it for our min/max function. It's actually relatively simple, but if you don't know what's going on, you might be a little confused. I recommend just sort of staring at pseudocode for a while until you actually understand what's happening here. Or, watching the video in the description over and over until you understand Or if you don't care about understanding what's going on, just move on, I suppose. So back in our event graph, we're going to need a couple of variables now that we have our minMax function. They are going to be integers, and they're just going to be the difficulty for our player 1 and player 2. So let's go player 1 difficulty and our player 2 difficulty. I'm going to make these instance editable, and for a value of 0, it's just going to be our player's turn. These difficulties, by the way, is just going to be how far ahead the AI looks when it's deciding what to do. So on begin play, after we get our available moves, if the AI's difficulty for player 1 is greater than 0, then we're going to have to let the AI decide its move and, well, play it. So let's get our minMax function. The graph is going to be our graph, and our depth is going to be our player 1's difficulty. Our alpha is just going to be a ridiculously low number. Let's go with negative, I don't know what exactly that is, but let's copy this. And our beta is going to be that, but positive. We are always going to be maximizing when we call our minMax function, and our AI is player 1 is going to be true in this case because, well, it's going to be the very first move. So player 1 is an AI in this case. After that, we are going to play the move. So in our play move, we are going to have to do some stuff when we actually finish playing our move. Our pieces finish flipping is called after all of this stuff because our pieces have to animate, and that takes time, and this all happens while it is animating. So after our pieces finish flipping, what we're going to do is check to see if we have available moves, so if the game is over. And basically what we're going to be doing here is we're going to be checking if our AI has to play a move or not. If there are available moves, and our player 1's difficulty or our player 2 difficulties is greater than 0 based on if we are player 1's turn or not, then we are going to have to call our minMax function again off this true, and then play the move that we get off of here. Once again, we are maximizing. Our graph is our graph. Our depth is going to be based on if we are player 1 or player 2's turn. Our AI is player 1 is going to be if it is player 1's turn. And our alpha and our beta is just going to be those ridiculously high and low numbers again. And doing this, I believe, should make it so that our AI can play moves. My bad, when we set our best move in our minMax function, we're not setting it from our minMax function's best move over here. We are setting it from our for each loop with break over here instead. So make sure this move is not connected to anything, and the sets are connected to this for each loop with break array element instead. So now if we go back to our level blueprint, I set my player 1 difficulty to 3, and if we hit play, the game should freeze up while the AI is thinking, and then it should play a move. So if we hit play, it sort of freezes up, and you'll see that our piece got flipped over here. Right here. This turned into a black piece because black moved first, and the AI placed a move somewhere, I'm not sure, because the piece did not get played, or at least the animation did not play. If I were to play right here, you'll see that this still gets flipped, because it knows that that's a black piece. But then this gets flipped to black because the AI played, I'm assuming, over here or here. It's one of these two. Now, the reason that's happening is because our play move doesn't actually tell the piece to appear and do all that stuff. That's done in our Othello board piece BP over here. When we click on our piece or our board over here, this is when it tells the Othello board that a piece is animating, and to set the visibility and our rotation of our piece, and to actually play the timeline for our piece falling. So we're gonna have to rearrange some of this stuff a little bit. So back in our Othello BP, on our play move, this is where we're gonna tell our piece to fall. So let's make a new custom event here, and we'll call this custom event something like, oh, I don't know, make piece fall. It's a very creative name. And this make piece fall is gonna be connected to our set piece is animating over here. Let's break these links, and on the finished, we're not going to do our Othello board play move. So back in our Othello BP on play move, we are going to get our containers array element at the chord to index and tell it to make piece fall. Let's add another custom event where all this stuff is going to happen. Let's see, we don't need this branch anymore to see if our available moves contains that move. We also don't need to set our flipping pieces count to 0 because that actually is taken care of in our pieces finished flipping. Let's make another custom event. We'll call this piece finished falling. And this piece finished falling is going to take in a chord, and that's just going to be the move that was played. And we'll connect this piece finished falling to our get affected pieces over here instead, and our chords are going to be connected to where this chord used to be connected to. So over here and over here. Or sorry, let's call this move. And now in our Othello BP, on our make piece fall in the timeline when it finished updating, we are going to get our Othello board and say piece finished falling. And the move, of course, is going to be our chord. On our on-clicked piece and board, we also need to do stuff for this, because otherwise the player can't actually play a move. So let's move these up out of the way. And let's clean this up a little bit. These are connected to our piece right here, so let's just connect these, give it its own piece instead of connecting to that one. So now on our on-clicked piece or board, if we can actually play a move here, we are going to get our Othello board and just say play move at our chord. So let's try to play this one more time. We hit play and the game should freeze up for a little bit, and there it goes. And now you see that the piece actually fell when the AI played its move. So let's play over here. It falls, and then you see the game freezes up, and then the AI plays its move. And if we set the AI for both of these to be a number, let's put these both at 3, you'll see that the game should sort of just freeze up always. It's basically always going to be freezing up because the AI is constantly going to be thinking about what move it needs to make. And that's obviously not great. And now we have an error/warning while playing in the editor. Now this error is saying that we have an infinite loop detected in our blueprints because our minMax function here is calling a lot of for each loop with breaks. It's calling a lot of loops in general. It's doing a lot of loops in general. In fact, if we were to go back to our Othello BP and set our player 1's difficulty to 4 and we hit play, it just wouldn't even play a move. It would cause so many loops in that very first iteration of our play move that it wouldn't even be able to play the very first move. So what's going on here is that Unreal thinks that we have an infinite loop because every time you do a loop, it adds to a loop counter. They sort of made it so that Unreal Blueprints doesn't crash as easily as it could compared to if you were doing C++. For example, if you were to call a function on a null pointer in Blueprints, it wouldn't crash the engine. But if you were to do that in C++, it would. They sort of put a lot of safeguards in Blueprints to make it so that you don't cause infinite loops or cause crashes when you call functions on null pointers and stuff like that. So there's a sort of workaround we could do. If we go to our project settings, I believe, and search for loop, you'll see that there is a maximum loop iteration count, and it's set to this number. I can't be bothered to count. If we were to add, just say, 2 zeros to this, and then hit play again with our AI having a difficulty of 4, it should be able to play. There it is. And you'll see that our AI is now able to play. It's really slow, but it's playing. Now that was technically a workaround, but it's not a great solution because you'll notice that the game still freezes when you're doing stuff because this minMax function is not multi-threaded. So it has to complete its syncing in that same frame. So the game will not continue rendering frames until this minMax function finds the move that it should play when it's get called. So the obvious solution would be to multi-thread our minMax function, but that's not something we can really do easily in Unreal Blueprints because there is no option to just say, hey, make this multi-threaded by default. There are a couple of plugins you could download. I'm not sure how to actually use them though. There is the multitask plugin. This is free. A generic multitask system for Unreal 4. I actually have no idea how to use this. There's no documentation as far as I can really tell, and I don't see any YouTube videos involving this plugin, so it's a complete mystery to me. I've played around with it for like 5 hours and I couldn't figure it out. Maybe I'm just missing something really obvious, but I seriously have no idea how to use this. There's actually also another plugin on the marketplace that allows you to multi-thread stuff in Blueprints, but I've never actually touched it because it costs $4.99, I believe, and I don't want to recommend buying stuff because I want everything we do to be free. I don't want to say, hey, thanks for coming all the way through this tutorial just to say, now buy this plugin, especially since I'm not going to be making any money off that plugin. You know, you could check it out if you want, but I don't know how to use it. Now, if you really want to multi-thread this, you could go into C++ and do like 5 lines of code to actually get it working. I did a video on it earlier, but in case you haven't watched it, I'll put a link in the description below. Anyway, so let's do one last thing. Right now, the player can actually play while it is the AI's turn, so let's take care of that. In our Othello board piece, we need to add another condition to this and to see if we can actually play a move or not, and that is going to be if our Othello board get player 1's turn. We need to check to see if the Othello board's player difficulty for our player 1 and our player 2 is equal to 0 based on if it is the player 1 or player 2's turn. So off this and, we are going to do a select, and that select is going to be if it is player 1's turn. And if it is player 1's turn, then we are going to send in our player 1's difficulty. If it is equal to 0, and that's true, then we can also play a move. Otherwise, if it is player 2's turn, we need to check to see if player 2's difficulty is equal to 0. Otherwise, if it is not equal to 0, that means it is the AI's turn, therefore the player could not actually play a move, so we won't actually do anything when we click on the piece. So let's just let the AIs play out for a little bit so you can see what the AI looks like when it's playing. I'm just going to go with settings of 3 and 2 for our player 1 and our player 2 difficulty, just to make this play a little faster. And there we go, white just got completely dominated. Black won with a score of 54-0 because black is looking ahead one more turn than white, which is apparently a really big deal. So let's actually incorporate this into our visual novel. We will save this level as, let's go with Othello, save in our maps folder, and in our dialogue, let's say somewhere over here when we say no, we're going to say, do you want to play Othello? We're going to add a speech option for yes, and let's add a node back to our do you want to move on to the next chapter, and that's just going to say no. Now in our yes, we are going to tell our enter events to say game instance. We're going to do a modify name. The name variable is going to be load level, and the name value for that is just going to be Othello. So if we save this and then go back to our maps for our new map where we actually have our visual novel, and then in our content browser in our game instance where we do our modify name value, let's add a pin for our load level. Off this load level, we're going to call open level, and the level name is going to be our name value we passed in. So if we compile, save, and hit play, we start, and then we go on to, let's just break it, don't want to move on, we do want to play Othello, and then the Othello map loads. And it loads with the AI being whatever it thought the AI was when you saved the map in our Othello BP. So what we could do is in our test dialog is when we say do you want to play Othello, we could save a integer in our game instance, for example. So we could tell our game instance to modify a class int variable, and the variable name, we don't have a int yet, so in our game instance let's add 2 new variables. This is going to be our player 1 AI and our player 2 AI, and they're both going to be integers. And back in our test dialog we can modify the name variable of our player 1 and our player 2 AIs to be whatever we want. So our player 1 AI, we're going to set that to be 0, and then our player 2 AI, we can set this to be whatever we want. So based on, let's say, the character we're playing against. So if we were playing against Yuri, we could set this to be like 3, or if we were playing against Aina, we could set it to be like 1. And that's how we can modify the AI difficulty of our characters. So back in our Othello BP on event begin play, before we do this stuff, we are going to set our player 1 difficulty and our player 2 difficulty to be based on our game instances difficulties. Something like that. So now if we hit play and start and then go to our Othello game, no, and then yes, the game doesn't move around because it's our turn now because it knows that our player 1 difficulty is 0, and our player 2 difficulty is 1. So we can play, and then the AI plays its move, and then we can play, and the AI plays a move, and etc. Now in our Othello BP, when the game is over here, we can tell it to just load our level again for our actual visual novel. Now that level name for me is called New Map, but you would probably have a different name for it. And you probably also want to display a widget saying like you win or you lose or whatever. But we're not going to bother doing that. So if we hit play and then start and then go to our Othello, say no and then yes. And I'm just going to speed through this really quick so that you don't have to watch me fail at playing Othello. And then you'll see it loaded this level, but then when it loaded this level, it brought us back to the main menu. And the reason it's doing that is because when we reach this node over here to actually load our level, it checks to see if there is a next node, and there isn't. So it says dialog stuck, no valid child for this node, and it's going to set our current dialog to be nothing. And if you remember, our menu checks if we are in-game based on if we have a dialog or not. So to fix this, let's just add another child over here, and then we try this one more time. And it's gonna say game over, and it's gonna load us back into our visual novel level. However, our visual novel is not showing up. And that's because when we do our event begin play in our VN game mode, we set the render opacity and the visibility of our canvas panel and stuff, but we never actually add it to our viewport again because they get removed from our viewport when we load the levels. So let's add these back to our viewport, the dialog widget and our menu widget. And if we try this one more time, and if we end the game, it brings us back to our widget, but it doesn't have any text here on this node. So let's add some branches to this. We'll add a selector child, and the selector is going to be based on if we won or we lost. So in our game instance, let's add a new variable. It's going to be a boolean, and it's going to be we won, or 1. It doesn't matter. And then in our Othello, when the game is over, we're going to check to see if our player 1 or our player 2 is our actual player. And we're going to check to see who the winner is. So if player 1 count is greater than our player 2 count, we are going to get our game instance, cast to VN game instance, and then set the 1 based on if we are player 1 or player 2 and if player 1 won. So do we select based on if player 1 won, and if player 1 did win, we're going to pass in our player difficulty equal to 0. So if player 1 difficulty equal to 0, then that means that is our player. And if our player won, then that's going to return true. However, if player 2 won, we're going to return if player 2 is equal to 0. Because this is going to return if player 2 is equal to our player or not. And then back in our test dialog, on our select, we're going to add some speech childs, and this first speech child is going to say you win, and the second speech child is going to say you lose. And they're both going to connect to a end child. And then the condition for you win is going to be if our game instance, check class boolean variable for our game instance for 1 is true. So if we try this one more time, it's going to bring us back over here, and if we click, it'll say you lose. We don't actually need this dialog anymore, this blank dialog that doesn't say anything. We don't need this because we can just connect this to here now. And we obviously don't want to have to click after we end the game, so in our Othello BP, before we load our level, we should probably also tell our dialog widget to move on to the next child. So let's get our game instance, get dialog widget, and then tell it to just choose option 0 before we load the level. Let's see what that looks like. Now we lose the game, and it brings us to you lose. Great. Anyways, that's going to be added to our history, the blank line, and you probably want to get rid of that somehow in your dialog. Maybe you will, in your choose option or something like that, you'll add a boolean that says, do you want to add this to your history or not? And then when you choose your option on your update text, you probably also want to have a boolean that asks if you want to add it to your history or not, and then over here we would branch on if we are adding it to our history. And obviously in this case we would say no in our BP and the choose option. We would say no to adding it to our history, but for everything else we would say yes, but I don't feel like doing it. Anyways, that probably does it for the mini game. Hopefully that showed you how to go to a mini game level and then back to our visual novel level. And I will hopefully maybe see you next time.